1.7, the precise definition of a limit. The intuitive definition of a limit is inadequate. The one we've been using, the one we've been talking about in the previous videos. That definition is inadequate for some purposes because such phrases as the type we've been using, x is close to 2, f of x gets closer and closer to L, are vague. Because we want to prove limits. We don't want to make tables and argue from tables and graphs. In order to be able to prove conclusively that the limit as x approaches 0 of something like x cubed plus the quotient of cos 5x and 10,000 equals 1/10,000th, that is 0.0001, or to prove conclusively that the limit as x goes to 0 of sine x over x equals 1, we must make a definition of a limit precise. To motivate the precise definition of a limit, let's consider the function. Okay, so we're going to use this example. It's pretty typical, and we're going to generalize from there to come up with a precise definition of a limit, to prove things are actually limits. So here's a piecewise defined function. It's 2x minus 1 everywhere except at x equals 3. I'm sorry, it's 6. Yeah. 2x minus 1 everywhere except at x equals 3, but at 3 it has a value of 6. So the point 36 will be by itself out there on the graph. Intuitively, it is clear that when x is close to 3, but x is not equal to 3, then f of x is close to 5. Right, put a 3 in there, and you got 6 minus 1, which are 5. So when x is close to 3 but not equal to 3, f of x is close to 5. And it should be clear that the limit as x approaches 3 of f of x equals 5. To obtain more detailed information about how f of x varies when x is close to 3, we ask the following question. Okay, think about this. How close to 3 does x have to be so that f of x differs from 5 by less than 1/10? Okay, so, if you get within some, small number distance from 3, then that forces f of x to be close to 5. How close does it have to be so that f of x differs from 5 by less than 1/10? The distance from x to 3 is absolute x minus 3. Okay, maybe you're not in the habit of translating an expression like this in this way, but it is the same thing. And the distance from f of x to 5 is absolute f of x minus 5. That's a translation. So our problem is to find a number delta so that absolute f of x minus 5 is less than 0.1 if absolute x minus 3 is less than delta, but x not equal to 3. We don't care about x equaling 3. We only need x to be close to 3. If absolute x minus 3 is greater than 0, okay, of course, that's true unless x is equal to 3 because absolute value can't be negative. If absolute x minus 3 greater than 0, then x is not equal to 3. So an equivalent formulation of our problem is to find a number delta such that absolute f of x minus 5, or we should just say the distance from f of x to 5 is less than 0.1 if the positive number absolute x minus 3 is less than delta. Okay, so we're trying to find a number delta such that the distance between f of x and 5 is less than a tenth whenever the distance from x to 3 is less than this number delta that we have to find. Now, a number that will work is 0.05, okay? So let's say, okay, let's just go with it and say, okay, let's suppose that we had a number 0.05, and we're going to show that that does actually work. That's a delta that we can use, okay, 0.05, and that's going to make this true, that if the distance from x to 3 is less than that number, 0.05, then the distance from f of x to 5 is always going to be less than 0.1. Because if that be the case, that the absolute x minus 3 equals 0.05, then let's just think about this part of it, okay? Let's think about what happens with this f of x minus 5 let's think about what happens. Oh boy. Let's get that pen going here. With this absolute f of x minus 5. Okay, what happens to this thing? That's an ugly bracket right there. What happens to that if we pick for our delta a number like 0.05? Well, what happens is, you know, what happens to this thing right here, it is that, well, what was f of x? F of x, remember, was given in the original problem as 2x minus 1. Okay, so what happens to this is that you have absolute f of x minus 5. This is f of x right here, this 2x minus 1. You start simplifying, excuse me, start simplifying, and it's 2x minus 6, negative 1 minus 5, negative 6. But you know, this is absolute 2 times the quantity x minus 3, and there's a rule that allows you to break up the absolute values in this way. And so it's actually 2 times the absolute value of 2x minus 3. And that's less than, well, less than, because x minus 3, the inside, is less than 0.05, okay, by our hypothesis. So we're saying if that's true, look at what happens, okay? So we're supposing it's true. We're seeing what the consequences are. What we have in our expression here is that it is less than 2 times 0.05, which is 0.1. Now that's a familiar number. That's important. We, you know, saw that before. So let's put all this together. absolute f of x minus 5 is less than 0.1 if 0 is less than absolute x minus 3 is less than 0.05. And that was the whole goal, right? We had to find a number delta, which we said, well, let's try 0.05. And see what happens with that. Well, in fact, we do get this conclusion of this conditional, that absolute f of x minus 5 is less than 0.1. And so that's going to be the answer, right? The delta is the 0.05. An answer to the problem is given by delta equals 0.05. That is, if x is within a distance of 0.05 from 3, it's pretty close, but we can do it, then f of x will be within a distance of 0.1 from 5. So that actually, I mean, I think you agree that that's a good answer. It does do the job. But, you know, like, how do you come up with that? Well, I'll just, you know, kind of spill the beans here, that the 2 comes from here, right? That was given in the problem. 2x minus 1, that was actually the coefficient of x in the original problem as it was given. Okay, and the 0.01 comes from here. And so those numbers put together in that way produce the perfect answer, 0.05. Now, will that always work in a problem like this? If we change the number to 0.1 in our problem, this is x to the first right a smaller here. Number, and so it's a linear function, and so you're always going to be able to do that if you have a linear function. We'll see that also in the next video. But the thing is, not all the videos in there, and, you know, because then not all the videos, 0.05, all the functions are linear. Okay. Then by using the same method, we find that f of x will differ from 5 by less than 0.01, provided that f of x differs from 3 by less than, and we do the same kind of division that we were talking about. Now we're going to divide not the 0.1 but the 0.01 by 2 and get 0.005, not 5/100ths but 5,000ths. And, you know, if we wanted to go one more 0, you know, if we wanted to take that decimal point out here, go one more time, make a stupid, confused face up there, then we would, you know, put a 0 in here and get 0.0005 for our delta. In that case, we would get 0.0005 for our delta that would work in that situation. So you can see how delta relates to this number that we're trying to, you know, the closeness that we're trying to get with f of x and a limit. The numbers 0.1, 0.01, and 0.001 that we have considered are error tolerances that we might allow. Okay, we're trying to get that 5 close. To be, we're trying to get the precise limit of f of x as x approaches 3. Yeah, we can always do it.
We
can
do it all day.
Only be able to
we'll
bring
just change
the
our
difference
x.
between f of
I'm
x
sorry,
and
change
5
our delta to make it
below
happen.
each of these three numbers. We must be able to bring it below any positive number. Okay, so if anyone says, "Oh, well, that doesn't prove it," what about 0.0000000001? Okay, can you produce a delta which makes the difference between f of x and 5.000000000001? Well, yeah, we can do it. I mean, we have a way of taking the difference and using that number 2 in a special way, the 2 that we were given when we were told in the original problem that f of x equals 2x, I guess it's minus 1, and we could come up with such a delta. And by the same reasoning, we can. If we write epsilon, the Greek letter epsilon, for an arbitrary positive number, then we find, as before, that statement 1, absolute f of x minus 5 is less than epsilon if 0 less than absolute x minus 3 less than delta equal to epsilon over 2. So what we're going to do is we're just going to say, okay, we're always going to make delta equal to epsilon over 2. Yes, it's that 2, that same 2. If that were 3 right there, we'd be saying epsilon over 3. But if we just make delta epsilon over 2, we're always going to be able to come up with a delta that works. This is a precise way of saying that f of x is close to 5 when x is close to 3, because this statement 1 says that we can make the values of f of x within an arbitrary distance epsilon, okay? As close as we like, arbitrary. Within an arbitrary distance epsilon from 5 by taking the values of x within a distance of epsilon over 2. Whatever that epsilon is, that arbitrary distance epsilon is, just cut it in half and we'll be able to come up with a delta that works. Within a distance epsilon over 2 from 3, but x not equal to 3. Note that statement 1 can be rewritten as follows. Okay, so now we're going to kind of say the same thing in a number of different ways. I encourage you to keep your concentration as you consider all of these different ways, because if you do that one time, then you will have give yourself a chance thoroughly to understand the precise definition of a limit. After that, then it would be okay to think about your favorite ways of saying that the limit as x approaches some number a of f of x is equal to L. Okay, so statement 1 can be written. We can take that absolute value, compound absolute value inequality, and you might remember from algebra that we can always write that. Really, it's just this part of it. Okay, as a compound inequality, x between 3 minus delta and 3 plus delta. Okay, basically we would be saying that negative delta less than x minus 3 less than delta, and add 3 to all three sides. So, but if that be the case, then we can write a compound inequality involving f of x using the same sort of algebra. F of x is between 5 minus epsilon and 5 plus epsilon. And this is illustrated in the figure. Okay, so here's our f of x equals 2x minus 1 graph. And here's 3. Okay, so x is approaching 3. And so if we, armed with our delta, our magic number delta, if we're within delta of 3, that is if we're between 3 minus delta and 3 plus delta, then in the vertical, we're always going to be less than epsilon from 5 in the vertical, okay, between 5 plus epsilon and 5 minus epsilon. By taking the values of x, which is not equal to 3, to lie in the interval 3 minus delta, 3 plus delta, we think of that as a small interval about 3. We can make the values of f of x lie in a small interval about 5. 5 minus epsilon, 5 plus epsilon. Now, we proved a limit about the function 2x minus 1 and the limit 5 and x approaching 3. Using this as a model, we give a precise definition of a limit. Okay, so here it is, okay? And you can save that as a picture, make it your desktop, memorize it, whatever, okay? It's definition 2 in Stewart. Let f be a function defined on some open interval that contains the number a except possibly a itself. Okay, so open interval, and so it's defined near a. Then we say that the limit of f of x as x approaches a is L. And we write the limit as x approaches a of f of x equals L if, okay, so now here is what makes that equation defined. If for every epsilon greater than 0, there's a number delta greater than 0, such that if 0 is between absolute x minus a less than delta, then absolute f of x minus L is less than epsilon. And you will get used to saying for every epsilon there exists a delta. Notice here that in this case they wrote the if-then in the more common order. Okay, if and then. We have been working with a then, and then the if. Okay, but it's saying the same thing. Okay, obviously the limit as x approaches 3 of f of x equals 5 is a special case of this definition. We just proved a specific statement, but we did prove that limit. Okay, so we've got our precise definition of a limit, and let's investigate it. Since absolute x minus a, that is the distance from x to a, and absolute f of x minus L is the distance from f of x to L, and since epsilon can be arbitrarily small, okay, as small as anyone wants, the definition of a limit can be expressed in words as follows. Okay, so this symbol, limit as x approaches a of f of x equals L, means that the distance between f of x and L can be made arbitrarily small by taking the distance from x to a sufficiently small, but not 0. Okay, and in the first problem that we did, we found that 0.05 was a number that was sufficiently small. If you get within that, then you're gold. Alternatively, the limit as x approaches a of f of x equals L, that symbol, the values of f of x can be made as close to as we please to L by taking x close enough to a, but not equal to a. So if you don't like the word sufficiently close, by taking x close enough to a, we can get f of x to be as close as we like to L. We can get values of f of x as close as we like to L if we make x sufficiently close to a. We can also reformulate definition 2 in terms of intervals by observing that the inequality absolute x minus a less than delta is equivalent to the compound inequality negative delta less than x minus a less than delta, and then you can add a to all three sides of that and get a minus delta less than x less than a plus delta. So if you like those compound inequalities, knock yourself out. Right here you can say a minus delta less than x less than a plus delta. Also, 0 less than absolute x minus a is true if and only if x minus a is not equal to 0. That is, x is not equal to a, because absolute value can't be negative. But absolute value can be 0, but it's not going to be 0 if x and a are not the same thing. Similarly, the inequality absolute f of x minus L is less than epsilon, that can be written as a compound inequality. L minus epsilon less than f of x less than L plus epsilon. So that clause in the definition you could rewrite if you prefer L minus epsilon less than f of x less than L plus epsilon. Therefore, in terms of intervals, definition 2 can be stated as follows. Okay, so now we're going to use intervals, not inequalities. And we know how to make a compound inequality like this into an interval. So f of x is going to be in the interval L minus epsilon, L plus epsilon. Okay, and something similar can be done with x. X is going to be between a minus delta and a plus delta. Arrow diagram version, okay? Think through all of these, okay? And then afterward, you'll be free to, think of the one that you like. You should actually memorize these words. And then the picture that's in your mind, you're free to come up with that the way you want. We interpret this statement geometrically by representing, my bad. I didn't mean you should memorize this version of it. Memorize the definition 2, and then the picture in your mind could be any of these pictures. Okay, so here's a picture, an arrow diagram. f maps a subset of the set of real numbers onto another subset of the set of real numbers. Okay, and so this number x is going to get close to a, and f of x is going to get close to f of a. In some cases, that'll be the same thing as L. Okay, so this is what you memorize. Okay, memorize that. Own that thing. Okay, the definition of limits says that if any small interval L minus epsilon, L plus epsilon is given around L, then we can find an interval A minus delta, A plus delta around A such that F maps all the points in that little A minus delta, A plus delta, except possibly A, into the interval L minus epsilon, L plus epsilon. Okay? Someone says, we want L to be in here. And you say, okay, I can always do that because I can come up with a delta so that if x is in this interval, we're always going to meet your standard of being within epsilon of L. Another geometric interpretation of limits can be given in terms of the graph of a function. If epsilon positive is given, then we draw the horizontal lines, y equals L plus epsilon and y equals L minus epsilon. Okay, so Mr. Mean Guy says, oh, you've got to make your y, your f of x, in that vertical interval of numbers. And so we're like, no problem. We can find a number delta, which actually is a function of epsilon, that will always get the job done. If the limit as x approaches a of f of x equals L, then we can find a number delta positive such that if we restrict x to lie in the interval a minus delta, a plus delta, if we can come up with a delta so that if we're in here, if we're in there, x is in here, then we're going to be within epsilon of L. We can get arbitrarily close to L by making x sufficiently close to A, within delta of A. So we can find a number delta positive such that if we restrict x to lie in the interval a minus delta, a plus delta, x not equal to a, then the curve, whatever it is, whether it be the line, y equals 2x minus 1, or anything else, y equals f of x lies between the horizontal lines, y equals L minus epsilon and y equals L plus epsilon. You can see that if such a delta has been found, then any smaller delta would also work. Okay, so we said let's let delta be epsilon over 2. Delta equal, you might have thought about this, okay? Delta equals epsilon over 2. That's always going to work. And we said, oh, ain't it awesome that if we let delta equal epsilon over 2, that's always going to work. Well, we could have, honestly, we could have said, let's let delta equal epsilon always over 3. And that would actually always work too. And so it would be a technically correct response. Not very artful, though, because we were able to write such a beautiful statement of the proof using that 2, the number that actually showed up in the original problem, as the coefficient of x in y equals f of x. It is important to realize that the process illustrated in figures 4 and 5 must work for every positive number epsilon, no matter how small it is chosen. Figure 6 shows that if a smaller epsilon is chosen, then a smaller delta may be required. Okay, so maybe they came up with a really small delta so that, the goal is to get f of x between these two horizontal lines. Okay, well, delta, this delta then is not necessarily going to be good enough, right? Because you could have a number right in here so that the curve is actually not close enough, f of x is actually not close enough to L. So a smaller delta may be required. So do memorize the precise definition of a limit. It will serve you well.